Let's begin. So for this video, we are going to be covering the tiered collision system. So as you see here, we have two Group AABBs, one for the axes, one for the frigates. Any frigates within the Group AABB of the axis have their B-spheres being drawn to have the second layer of testing done. If I were to move in a bit closer to showcase that testing, we can see that once the OBB is close enough to the axis, its B-sphere is being rendered, and then we do the actual collision test once we have all of that in. So that is the last step. Same thing goes for the if I were to just quickly move that out of the way. So now we have the AABB. AABB does the first initial testing here. So I see only the AABBs colliding with it. And once we get close enough, we have a successful intended collision test here. If I were to move the OBB and AABB out, you can see their B-spheres are not being rendered anymore because they no longer pass that group test. If I back out all the way, the group AABBs are no longer colliding. The last part to cover is in self-testing. So this skips the testing of the group AABBs because all frigates are within the same group. We get close enough to get the B-spheres successfully colliding, and then we can test for the actual collisions. So here's the AABB successfully testing, and here is the OBB successfully testing. Right there is your collision. Alright, so for covering this, first with the collidables, there are now multiple types of collision volumes you can use. This passes in with an enum type of B-sphere, ABB, or OBB. There's also a B-sphere that is a part of all collidables now to be part of the tiered testing. If you were to choose OBBs, there are some default data that you have to pass in at the beginning, which will be calculated once and then never again. It never needs to be updated. So here I'll just talk about for OBBs, when you compute the data, you get the world matrix and then update both its center and scale square factor. Once you have your model type, whenever you want to update the collision data, you update the intended collision volume, and then you also update the B-sphere's collision volume, because again, this is part of the tiered testing. For the intended collision volume, we'll just go to AABB. For that involves looping through all the points on your vertex list for the model, finding the minimum min and maximum max. Once you find both of those, you just set the min and max to be that, and that is what you have. You can also update the half diagonal and world center, which you just quickly cover. Both the AABB and OBB are part of a collision box type. This is just where I have some getters and setters that are consistent, all documented. So over here, just some setters and just some getters, specifically no setters, because the AABB and OBB have unique ways they need to set their data, which is calculated in the compute data step. So yes, that is everything for the collidable. Collision groups now have a group AABB. This is updated once per frame, which I'll showcase in the collision manager. Oh, I didn't showcase B-sphere. For B-sphere computing data, which is used by the group A, helpful for the group AABB, we can get the minimum and maximum for the B-sphere. This is just adding the radii to get a scuffed AABB wrapped around the B-sphere, and this scuffed AABB is used by the collision group, which will loop through all of its B-sphere group objects, B-spheres, get the min and max, find the minimum min, maximum max, and then compute the data using the minimum and max to get the AABB wrapped around all of the objects of the same type. This is then used by the collision manager during the process element step, which is done once per frame in the scene update loop. If I were to just show all references, this is only ever called once during the scene update. It will loop through all of its collision group types in its vector. If it exists in the scene, it will call the update group AABB, otherwise it skips it. And once we have all of that, we can then execute all of our collision tests. Speaking of the collision tests, these are tiered testing steps. So for collision self, we have a 2-step process, which is documented, and the collision pair, we have a 4-step process, which is also documented. So for the collision pairs, we'd compare the two group AABBs and use the visitor pattern on them. This visitor pattern allows us to do the proper testing without having any if statements. So this AABB does not know what type the other collision volume is. So we have the other collision volume, which knows what type it is, visit the intersect for its AABB. So in this case, it is also an AABB. So this AABB will call visit intersect on AABB, which is done right here with the math tools. That is how all the visitor patterns work here, where it's just the B-sphere says, hey, I don't know what you are, but you do the test on B-spheres. And that's how all the collision volume tests work. So back to this, we test the group AABBs. If that passes, we test the B spheres of all collidables in one group against the AABB group of the other group. For every collidable that passes that test, we test their B sphere once again on all the B, except this time on all the B spheres within that other group. For every collidable passing that test, we do the actual intended collision volume. And if all of those tiers work, we send the collision. This allows us to reduce the amount of pairwise testing we do and break out early. Lastly, for these collision tests itself, we skip the group AABB testing because we do not have any other AABB to test to. All objects within the self-test are sharing the same group AABB, so they pass the tests immediately. So we start by testing the B sphere, and if that works, we do the intended collision volume. Lastly, for the math tools, just to showcase the testing. So we have B sphere to B sphere. We already know about that from last semester. Just get the vector from centers and get the less than the radii distance squared. For B sphere to AABB, we clamp the center of the B sphere to the AABB. If the clamp point to the center is less than the radii squared, you have a collision. B sphere to OBB, we move the B sphere into the OBB's local space, clamp the point like we did with AABB, move it back to world space. If the distance from that point to the sphere's center is less than the radii squared, you have a collision. For B sphere, the segment as an actual content, we end up getting the vector that creates the segment, compute the time t relative to the sphere center and the point 0 of that segment, clamp that value between 0 and 1, get the actual point at the time, compare that point with the sphere center. If the dot product of that nearest point is less than the radii squared, you have a collision. As an additional step, if you want the intersection points, it will do the quadratic equation on the other point and pass in the intersections here. If the part underneath the square root is negative, we can break out fast because we know we do not have any collision points. Next up, AABB to AABB. This is just testing over X, Y, and Z axes, making sure there's overlap on all of them. If any of these axes show that there is no overlap, we do not have a collision, so we can break out. So for AABB to OBB, we end up getting the world in half diagonals. We're going to be computing the projection on an axis, so doing that is involving getting the local axis and multiplying by the half diagonal. If the sum of X, Y, and Z of that diagonal divided by the mag and multiplying by the scale squared, that is the float value that we return. If that value for both of the local axes, so for the AABB and the OBB, if that value is less than the distance between them, if that is less than or equal to, then that means that there is no gap, we can move on. If this value is greater, there's a gap, we break out immediately. To determine the axes, we take the we do the SAT theorem. So we have the XYZ of world 1, XYZ of world 2, compute the cross products between all of them, and that's all 15 axes we have to test. So we, like I said, we loop through. Because this one is the AABB testing, there's no need to multiply by the inverse world for the AABB. It is already in world space. OBB, we have to do that multiplication to get in world space. We compute the max projection distance for both of them using the projection on axis I just showcased up above here. Right over here, we'd use that. And then if the sum of those two is less than or equal to the distance, we have no gaps, we can continue. If we find a gap, we can break out fast because this part will return false, and then we return whether or not we found a gap. For OBB to OBB, it's the same exact process. However, the only difference is both of them are in local space. So now we have to apply the inverse world. And that's it.